Okay, in Chapter 7, we're going to discuss orientation tolerances. So your objectives are to be able to identify, apply, and interpret orientation tolerances. 2, complete orientation tolerance specifications, including 1 or 2 datum feature references. And 3, explain the effects of material condition modifiers where orientation tolerances are applied to features of size. And 4, calculate the virtual condition for internal and external features of size to which an orientation tolerance is applied. And 5, complete tolerance specifications that include orientation and form requirements in a single feature. And 6 are definitions of terms. Okay, orientation tolerances are specified to specify the allowable orientation variation of a feature relative to one or more datum features. So orientation has to do with respect to one or more datum features. So there are only 3 orientation tolerances. There's perpendicularity, parallelism, and angularity. Orientation tolerances are specified using a feature control frame and may be applied to surfaces and to features of size. So the method of application determines whether the tolerance establishes a requirement on a surface or a feature of size. Specified using a feature control frame will always be done, and orientation tolerances can be applied to surfaces and they can be applied to features of size, and it's always referenced to at least one datum. Orientation tolerances are referenced always to at least one datum. So here are our orientation tolerances. Like I said, there's only 3. Angularity, here's the symbol. Parallelism, here's the symbol. And perpendicularity, and there's the symbol. Rather intuitive symbols. So let's look at feature control frames and what they look like. Here we have a perpendicularity tolerance. The tolerance symbol is in the first block, the tolerance value is in the middle block, and then the datum feature reference is in the far right block. Okay, so here we have just an orientation tolerance. Here we have a form tolerance, which refines an orientation tolerance. Okay, so in this case, we have a orientation tolerance of 12 thousandths perpendicularity, and then we have a form tolerance on top of that. So therefore, that surface that has to be perpendicular also has to be flat within form. Here we have an orientation tolerance, this perpendicularity, as a refinement of a position tolerance. So here we have a position tolerance, and then that position tolerance is further refined by this orientation tolerance. So that could be a hole, in which case we are identifying the position of this hole with a geometric tolerance, and then we can refine that tolerance by using a perpendicularity tolerance. Now, we talked about virtual condition before in previous chapters, and it will always come up again. So MMC, applied to a feature of size, establishes a virtual condition. A virtual condition of mating parts are equal or provide a clearance to enable ease of assembly. So that's why we do things with maximum material condition and maximum material boundaries in GD&T, is because we are assuring that the parts will assemble. Internal features. So an internal feature, you would take the MMC and you would subtract the orientation tolerance. Whereas an external feature, for the virtual condition, you'll take the MMC, the maximum material condition, and you'll add to that the orientation tolerance. Okay. We've had these exercises before. This is a very important point. What we need to do for internal features, we need to subtract the orientation tolerance from the MMC to get our virtual condition. And for external features, we need to add. Take a few minutes to get that point straight in your mind. Okay, so virtual condition, what we're talking about here is material condition and material boundary modifiers. So in this case, we have an orientation tolerance, this angularity. We have a tolerance here with an MMC modifier. And then we also have a maximum material boundary modifier on the datum feature. The material condition modifier is applicable to the orientation tolerances on a feature of size. So this would be a virtual condition. Okay, so virtual condition. When an orientation tolerance is applied to a feature of size with an MMC modifier, here's what happens. Okay, so this would be the drawing requirements. We have a slot width here, which is 375 plus or minus 7, and it has a perpendicularity, an orientation perpendicularity tolerance of 6 thousandths at the maximum material condition with respect to datum A. Okay, so in here we have datum plane A on the part. Here's our virtual condition, which is 362. Our virtual condition, this is 668, which is our maximum material condition, which would be the smallest slot, minus the 6 thousandths perpendicularity tolerance, and that gives me a virtual condition of 362. Okay, so as we see right here, we have a 362 is our virtual condition. And then what we're showing here, this is kind of like offset at an angle. So 368 is our maximum material condition. And then 362 is our virtual condition. So what that allows us to do is apply this perpendicularity tolerance to get from 368 down to 362. So therefore, the tolerance at MMC of the center plane of our slot becomes this 6 thousandths tolerance zone. So that is the effective perpendicularity tolerance on a slot at MMC. Now, if we were to take that same feature and not apply it at MMC. Okay, so I want you to take some time to compare these two slides very carefully. So first of all, this one here is we're applying the MMC, and here we have a virtual condition. Over here, everything is done RFS. If you notice here, we don't have an MMC modifier in our tolerance, and we don't have the MMB modifier in our datum. Okay, so what we have here is 375 plus or minus 7, and we have a perpendicularity tolerance that applies regardless of feature size. Okay, so what we have is we have a center plane of the feature. We have an unrelated actual mating envelope. We have datum plane A again. And then we have a 382 max and a 368 MMC. And then we have our 6 thousandths tolerance zone. So this is completely different when we're applying this with RFS. We don't get the bonus tolerances that we get here. What we have to do is we have to check both of the size, and we also have to check the perpendicularity separately. So that's what that means. Parallelism interpretation on a surface. Orientation between a flat surface and a datum plane may be specified with a parallelism tolerance. So this is a parallelism tolerance specified to a surface, not a feature size. So the size tolerance between the parallel flat surfaces establishes the orientation. So this is a note. A parallelism tolerance defines the allowable orientation variation between the tolerance feature and the reference datum feature, but does not affect the location or size of that feature. Okay, so what I'd like to do is stop this one here and pick this up in the next movie.